It's my good pleasure to talk about my research in this new AAAI new faculty highlight program. I'm Simon Du. I'm from University of Washington. Today I'm going to talk about my research on the ultra-wide neural networks and the neural tangent kernel. So let's review what neural network is. We all know that neural network is very popular in many applications. For example, we can use a convolutional neural network for computer vision tasks like image classification. We use graph neural network for bioinformatics datasets. We use recurrent neural network or attention-based neural network for natural language processing tasks like machine translation. We use general fully connected neural network for this general feature-based data sets. For example, we can use some features of an apartment to predict the price of this apartment. And we all know that neural networks are powerful for solving reinforcement learning problems. And here we'll use policy network or Q network. So in this talk, I will mostly focus on the supervised learning setting, which is the most powerful setting using neural network. So in this setting, we often have n data points sampled from some distribution mu. And each data point consists of x-y pairs, where x is input. It can be the sentence of the source language, a molecule, or the image. And the output y is what you want to predict. For example, sentence of the target language, some toxicity of the molecule, or the type or the category of this image. That's your output. So to find this good prediction function, often we solve a optimization problem like this. So here we'll use some loss function. We often call it L, which takes your prediction and the true label y and measures how well you predict on y. Okay, and we will search over all possible neural networks. For example, where we denote this as big F. And we find one neural network with certain parameters that can minimize this loss. Okay, so this is how we find a good neural network using this optimization procedure. So what we really care about is this generalization error. That is, we found one function, one neural network, small f, and want to know that how well it performs on a new data. Okay, so here we measure the generalization ability in terms of the expected loss of this prediction function, where the expectation is over the underlying distribution mu, which generates your training data. Okay, so this is the basic framework of supervised learning. And we all know that using deep neural networks for this kind of task, predicting the target language, like toxicity and category of the image, using neural networks is a very successful approach. So all this looks great. However, if you look at how people achieve these successes, it's actually not that pleasant. It's sometimes quite painful. So for example, suppose we want to build a learning system for image classification or say an engine to play some games. The first step is to choose your prediction functions model class, like what is your model. For example, here we can choose the neural network as your model. Okay. However, we are far from that yet. After choosing model, there are many engineering choices we need to pick in order to build a very strong prediction. Okay. Here, for example, we need to choose the architecture of the neural network. Should it be fully connected, convolutional, recurrent, residue, and we need to choose the depth, the width. We need to choose some particular optimization algorithm to find parameters of the neural network, like stochastic gradient descent, ADA-grad, or ADAM. And furthermore, we need to tune the learning rate and add, say, batch normalization, layer normalization, these techniques to improve the performance. And all these engineering choices are very important to determine the final performance. So in practice, we'll find many graduate students, they will tune these hyperparameters on many GPUs in order to find the best set of hyperparameters that let neural network perform well on the unseen data. So many people joke about this procedure, graduate student descent, because for the graduate students, it's really a painful experience. Okay. And that's why some people call neural network alchemy, because we don't know why this hyperparameter affect the final performance of the neural networks. And we don't know what the theoretical principle behind the neural network that makes the neural network so powerful. And furthermore, we don't have the theoretical foundation that based on which we can improve the neural network in a principled way. So my research aims to build the foundations of the neural network. And in this talk, I'll first talk about the foundations of deep learning in terms of the optimization and generalization ability. And importantly, I will relate this generalization and neural network and to a kernel method, which is a new kernel function. It's called neural tangent kernel. And we'll use this connection to understand the optimization and the generalization ability of the neural networks. And the second part, I'll talk about this new kernel, neural tangent kernel, how it behaves in practice. So I'll talk about 3 examples of fully connected neural tangent kernel, graph neural tangent kernel, and the convolution neural tangent kernel. So let's begin. So there are 2 fundamental questions about deep neural networks or general learning theory. The first is on optimization. So why we can find a neural network that can minimize this empirical loss over this n training data points. And second question is on generalization error. Why the neural network you find through solving the optimization can behave well on the unseen data, which is this expected loss. So let's first look at the optimization error. There's a big gap between the theory and practice. So in theory, for example, we consider a quadratic loss, and our function is this neural network function, which we denote as this f theta x, where theta is the parameter of the neural network. So theoretically, this is actually a highly non-convex function. There are many local minimum, saddle points, which can prevent you to find the global minimum. And finding the global minimum actually is an NP hard problem. So that's pretty bad. On the other hand, in practice, people will just use a very simple algorithm, gradient descent or its variant, to solve this highly non-convex function. And for gradient descent, we just use a negative gradient to update the parameter iteratively. So now let's look at what happened in practice. Actually, in practice, gradient descent solved this non-convex function very well. So this is an experiment done by Zhang et al. In 2017. So they try using gradient descent on an image data set and to optimize a neural network. Furthermore, they tried 2 setups. One is using the original data. The other one is to replace the labels in the data to wise with some random labels. So in this new setup, there's no even correlation between the input and the random labels. What's surprising is that they found just running this simple gradient descent algorithm, using both true labels or random labels, gradient descent can find the global minimum of this highly non-convex function. Okay, so that's quite surprising because we know this is actually an NP hard problem. So why is this the case? So one key difference between the existing theory and the modern use of neural network is that modern neural networks are highly over-parameterized. That is, the number of parameters in the neural network is much larger than the number of data in your training dataset. For example, for the CIFAR10 dataset, we have 50,000 data points, and the number of parameters is more than 1 million. And for the ImageNet dataset, we have 1.2 million data points, and the state-of-the-art model has more than 600 million parameters. So this phenomenon that the number of parameters is larger than the number of data points is called over-parameterization. So existing theory on, for example, the NP hardness only applies to small neural network. Actually, this does not. This theorem does not apply to this modern neural network. So there's no contradiction here. So when the number of parameters is bigger than the number of data, we know that there exists one neural network that can fit all the data points because you have more degree of freedom, and this is called neural network expressive power theory, and there's still a popular research direction. However, this kind of theory does not explain why gradient descent can find a neural network that can fit all the data points, okay, to achieve the global minimum. All right, so the overparameterization can help optimization. It can lead to another problem, which is the overfitting problem. We all learned from the first course of machine learning or statistics that if you want to generalize well, you should not let your model to be too complicated. Otherwise, cannot generalize well. So one standard characterization of the generalization error is that it is bounded by square root of some complex measure of your model divided by n, where n is your number of data. So here, the complex measure, usually you can use the number of parameters or more generally VC dimension to characterize this complex measure. However, in the overparameterization regime, the number of parameters is much bigger than the number of data points, so which makes this term very, very big. And furthermore, actually in practice, if we increase the number of parameters, the generalization error actually decreases. So these experiments show that this number of parameters is not the correct complex measure to characterize the generalization error of this more than overparameterized networks. And we need some new complex measure here. So here are the two fundamental questions we want to answer, and this is also what my research is about. Why does overparameterized deep neural network trained by gradient descent achieve zero optimization error, which is the global minimum of this highly non-convex function? And secondly, why does overparameterized deep neural network trained by gradient descent achieve very small generalization error, which we can observe in practice? And we'll need some new complex measure to characterize this small generalization error. Okay, so the main takeaway message from my talk is that what we can prove, the overparameterized network trained by gradient descent is actually equivalent to a kernel. Okay, so this is kind of surprising because we know that neural networks are very popular in recent years and kernels were popular before that. So we can actually prove that these two most popular methods in the last 20 to 30 years are actually equivalent in certain regime. So our condition is under certain is in certain regime of the parameter size. Okay, so let me give you a quick recap of what kernel method is. So for kernel method, we use a feature map phi, which maps the input to a high-dimensional feature space, such that in the high-dimensional feature space, the problem becomes easier. And for kernel function, we mean that we don't need to compute this feature map explicitly. All we need to compute is the kernel function between two feature maps of two inputs. And the kernel method is very popular. It can be used in computer vision, bioinformatics, synchronous processing, etc. So what we can prove that this overparameterized neural network trained by gradient descent is equivalent to a kernel, but this kernel is a new kernel. It's not like the classical kernel, like Gaussian kernel or polynomial kernel. It's actually equivalent to a new kernel called the neural tangent kernel, which I'll introduce later. Okay, so let's first look at the optimization. So this is our formal theorem. We can prove that if the width, which is the number of neurons for the fully connected neural network, or number of channels per layer for the convolution neural networks is very, very large, say poly n, then gradient descent on the overparameterized neural network converts to global optimum, which has zero optimization error. And our theorem holds for arbitrary labels and holds for arbitrary architectures, including fully connected neural network, convolution neural network, residue network, etc. So our theorem is very, very general. Basically, we prove that for ultra-wide neural network, as long as you apply gradient descent, you can find the global minimum. And this global minimum has zero optimization error. You can fit all the data points. So here we basically can explain the phenomenon observed in this Zhang et al.'s paper that even if you use random labels or true labels, you can find the global minimum. So there's some concurrent work by Alan Zhu et al. And Zhou et al. You can also check their results. They are very similar to ours. So this is our main result for the optimization. Our second result is about generalization. Okay, so for both results, we use the connection between neural networks and kernel to prove this theorem. Okay, for the generalization error, what we can prove is that again, if the width is bigger than say poly n, then gradient descent on the overparameterized neural network achieves generalization error at most square root 2 times y transpose h star inverse y divided by n. So this is a kind of a little bit complicated term, but let me explain it. So y here is an n-dimensional vector which corresponds to the n labels of your n trained data points. And h star corresponds to the kernel matrix of the training data points. So each entry of this kernel matrix is the kernel value of 2 inputs. So you can see here, this is very different from the classical generalization bound, which, for example, depends on the number of parameters in your network. This is actually a data-dependent bound. You can see here, it depends on your training data. It depends on the y, which is your labels, and h star, which depends on your input. And here, our bound does not depend on any kind of basic dimension or number of parameters. It only depends on your data. So here, to verify that our generalization bound actually characterizes the trend of the true generalization error, we use the evaluation strategy in Zhang et al.'s paper, where we add some random labels in the neural network, in the training data set. So as we know that if you add more random labels, because there's no correlation between input and random labels, you add more random labels, your generalization error should increase. And here we consider 2 error metrics. One is L1 error, one is the classification error. And you can see here, as we add more random labels, the generalization error also increase. And here we just plot our generalization error bound, so we can actually compute this volume. And this corresponds to this blue line. So you can see here, our generalization error bound also increases as we add more random labels. And this trend matches the true generalization error pretty well. What we want to emphasize here is that the classical generalization error bound, for example, the number of parameters, cannot explain this trend because they are data independent bounds. They do not depend on the data. But here, our generalization bound is a data dependent bound. So our generalization bound will change, and we can characterize the true generalization error very well, which cannot be achieved through the existing generalization error analysis. All right, so here in both optimization error and generalization error, we use the connection between neural networks and the neural tangent kernel. So what is neural tangent kernel? So this is the formula of the neural tangent kernel. Basically, if you give me any neural network function, we can give you a kernel function, which takes 2 inputs. So this is the definition of neural tangent kernel. So it depends on the gradient of the parameter at a specific point. Also, it depends on how you initialize your parameter. So this W here is an initial distribution of your neural network parameters. So this formula is very general because it applies to any neural network architecture. Give me any neural network architecture like FNN, I can give you a corresponding kernel function. Actually, different neural network correspond to different kernel as well. So this kernel function is first proposed in 2018, and by Jacob et al. They gave this name neural tangent kernel. And there's some other works also mention this kind of kernel in their work. So my work's main contribution is that we really prove that in terms of optimization and generalization properties, the neural tangent kernel and neural networks are equivalent. Okay, so that's our main theoretical contributions and can expand the optimization and generalization error of the neural network. So now the natural question is, okay, so you show that neural tangent kernel is equivalent to these deep neural networks. So what about applying neural tangent kernel directly? What's their performance? So this is the second part of my talk. So I'll give you some examples showing that this neural tangent kernel is a very strong classifier. So let me emphasize again that our main message is the overparameterized network trained by gradient descent is equivalent to this neural tangent kernel. And this equivalence is also useful for designing new kernels. Okay, so let's say you give me any neural network architecture, I can give you a neural tangent kernel formula, and this neural tangent kernel formula you can compute it explicitly. There's a dynamic programming approach to compute this neural tangent kernel explicitly, so you can use it directly for kernel regression or kernel support vector machine. Okay, and it's very general that you can transform, for example, fully connected convolutional graph neural network to its corresponding neural tangent kernel. So let's first look at the fully connected neural tangent kernel for the feature-based data. Remember, fully connected neural network is often used for this general feature-based data. So here, neural network takes one vector as an input, and here our kernel takes two vectors as input and computes the kernel module. Okay, so let's call it fully connected neural tangent kernel. So this is our experiment to verify that neural tangent kernel is really a strong classifier. So here we are inspired by an experiment set up by Fernandez Delgado et al. In 2014, where they tried more than 100 classifiers on a large number of UCI datasets, and they measure the average performance of each classifier on each dataset. Over each dataset. So to consider several metrics, including average rank, the lower the better, average accuracy, P95, PMA, the higher the better. And they found that the random forest in 2014 is the strongest classifier among all classifiers, okay, in terms of these metrics. And there's a recent work by Olsen et al. In 2018. They tried more than over-parameterized neural networks on the same datasets. And what they found is that the fully connected neural network performs well. So among the top classifiers, although it's not as strong as the previous champion, the random forest. So here, we just replace the fully connected neural network by its corresponding fully connected neural kernel. Okay. So the main difference between the fully connected neural network and fully connected neural tangent kernel is that we don't need to use random initialization, because remember in the kernel we already integrate over this expectation or over this initial distribution. So our predictor, the fully connected neural tangent kernel, is a deterministic predictor. So that makes this more stable than the fully connected neural network. And as a result, this fully connected neural tangent kernel is actually more perform better than all other classifiers, including the previous champion, the random forest, in terms of all the metrics: average rank, average accuracy, P95, PMA. Okay. And what we want to emphasize here is that this 90 data sets from the UCI database have a lot of categories, including finance, healthcare, etc. So a strong performance in the average sense means that this neural tangent kernel is a very strong classifier, off-the-shelf classifier. And if you have a new data set, you want to try something, you should try this neural tangent kernel. So this is our experiment on the feature-based data. Our second experiment is on graph classification. For example, you can model predicting the toxicity of a molecule as a graph classification problem. Okay, and it's also very useful for other social network and bioinformatic tasks. So for graph neural networks, a very popular method to classify graphs, which takes a graph as input and can automatically take the the neighborhood information of this graph as a source to do well in prediction. Okay, and here we can transform the graph neural network to graph neural tangent kernel. Okay. So here the kernel will take two graphs as input and output the real number. And you can use this function to do kernel regression or classification. So here we'll use it for graph classification. Okay, so here's our result. We try several benchmark data sets, including some social network data set and one bioinformatics data set. And we compare our graph neural tangent kernel with existing graph neural networks like graph convolution neural network, graph isomorphic neural network, and other existing graph kernels like WL kernels. And on this benchmark data sets, you can see that this new graph neural tangent kernel is really a strong performing classifier. It beats all the existing methods in all these benchmark data sets. So this means that this graph neural tangent kernel is a very strong classifier, and if you have a graph task, you should try it out. All right, another experiment we try is on this few-shot learning task, where we design this convolution neural network kernel. So the setting is like this. So it's a few-shot learning on the VOC7 dataset, which has 20 classes, but each class only have 1 to 8 examples. So the standard practice for this kind of few-shot learning is first to learn representation using, say, pre-training datasets. For example, we can train address 50 on the ImageNet as a feature collector. And then for the VOC7 dataset, we just use the linear SVM to just kind of fine-tune on this new dataset. Okay. And here, our main modification is that we just replace this linear SVM with a convolutional neural network kernel. Why we should use this? Because this is actually an image dataset, so we should use a convolutional operation in our prediction. Okay, even if it is in a few-shot learning. But the kernel does not have, or SVM does not have this property, so we use a convolutional neural network kernel SVM. So it's a kernel SVM, but the kernel is a convolutional neural network kernel. So you can see here, for all the setups, we can achieve some improvement. And on some setups, for example, in the 7 number of shots, we have a big improvement. Okay, so this shows that for the image dataset, and especially in the few-shot learning scenario, you should try this convolutional neural network kernel, and it can be drop-in classifier to replace the original linear classifier, for example, SVM, in your task. All right, so let me conclude my talk. So the main message that in certain regime, the over-parameterized neural network trained by gradient descent is equivalent to this neural network kernel. In terms of theory, we can use this equivalence to understand optimization and generalization properties of the deep neural networks. And in terms of applications, we can use neural network kernels to do classification, and it's actually a very strong classifier. So that's conclude my talk, and thanks for listening.